Welcome back, everybody. Well, lately we've been doing a lot of integration, and oftentimes our integrals have involved vector fields. Today we're going to focus in on vector fields and think physically about these. We're not going to worry so much about integration right now, but we're going to ask the question, how can we describe how our water is moving? And so here the idea, what water am I talking about? The idea is that our vector field here, this bunch of green arrows for our vector field F, we want to think of as describing some sort of fluid flow, right? So we have some fluid moving around, in this case the plane, but it could be 3 space or whatever, right? And these vectors are showing us, where the fluid at that point is moving and how fast. And so if we have this physical idea of what our vector field is describing, we'd like some way to describe some physical aspects, some behaviors, some characteristics of this fluid flow. And today we're going to introduce 2 mathematical objects that can help us do that, the divergence and curl. And we're going to start out just by introducing the definitions to these and getting a feel for how these work, and then we'll talk about what these actually mean and what they're describing. Okay, so to start off, here's our definition for divergence. So if we have a vector field here over 3 space, then the divergence of that vector field is the scalar function. Here scalar is just telling us that our function spits out numbers. The notation is div f, and it's px plus qy plus rz. So just those 3 partials added up, the x component with respect to x, the y component with respect to y, and the z component with respect to z. And so we can just put this to work. Here's a vector field on 3 space with this vector field. Its divergence through this definition, right? If here is our P, our Q, and our R, well, following our definition, taking the partial of P with respect to X, we're going to see just Y times e to the Z. Partial of 0 with respect to Y is 0, and partial of R with respect to Z, we would actually need product rule, right? Because we have Z's down at the bottom and up top. And so here, if we take the derivative of the bottom piece with respect to Z, we'll get Y, leave the exponential alone, then do the opposite, leave the YZ alone, take the derivative of the exponential, that'll just give us e to the Z. And so, I guess if we wanted to simplify this, we actually have 2 of these y e to the z's, then plus the yz e to the z. So there it is. There's our divergence, and notice it indeed is a scalar function. If we plug in any x, y, z point, this thing is going to, at the end of the day, spit us out a number. Now, one note about the divergence is that there's a nice kind of shorthand way that we can write it. It depends, though, on kind of thinking about maybe an odd-feeling vector. So the idea is, if we write this triangle called a nabla as a vector containing just our partial derivative operators, so not of a particular function, but just the operators, then I claim that we can write the divergence of f as this nabla dot producted with our vector field. And And just to see that this indeed is giving us what we want, right? Our vector field F, right, that has these three components, P, Q, and R. Well, how do we dot product two vectors, right? We take their x components and multiply them. And so here this would actually give us the partial derivative of p with respect to x. And similarly, when we multiply the middle components, we'll get qy, and the z components we get rz, and we'd add them up, right? And so indeed, this nabla dot f, or this nabla is also called del dot f, does indeed hand us exactly what the divergence of f is. The second object that can help describe some physical behavior of our fluid flow is the curl of a vector field. And so here's our definition in this case. We have a vector field on 3 space. Then the curl of f is the vector field. So it's another vector field. Curl of f, where here, notice we can write this just by taking the divergence definition, which was del dot f, and replacing the dot product with the cross product. And I claim that this gives us the curl of f. And so there is a big, long definition that we could write down for what the curl of f equals, but I'm not going to write it down. What's cleanest is to think of computing this using our little determinant mnemonic for computing cross products. And remember, this goes as such. We have our I, J, and K going across the top, and then our left vector here, its components give us the middle row, and then our right-hand vector, its components give us the bottom row, right? And we go through and compute the determinant, as we would if we were just taking the cross product of two vectors. And so let's put this to work. So here's our vector fields from above. Let's compute its curl. Well, just feeding into our mnemonic here, we have I, J, and K, our partials, and then just the unaltered components of our vector field down here. Right, if we want to take this determinant and figure out what goes in the first component, right, that's us looking at this I, and so we want to forget what comes in that column and that row, and we're just going to take the 2 by 2 determinant of this smaller box, the smaller matrix that we have, right? And so doing that with the AD minus BC formula, we would be told to take the partial with respect to y of this function minus the partial with respect to z of this function. And so, taking those partials, well, the partial with respect to y over here is just z e to the z, and then the partial with respect to z of 0 is just 0. And here I've taken the liberty of giving us that negative that needs to go in the middle component of any cross product to start. Why don't you pause the video and see if you can, following the determinant, figure out what goes in each of these next 2 components for our curl. All right, well, for our middle component, right, we're now thinking about this J, and again, we're not going to forget the row that it lives in and its column. And so here we have these kind of 2 sides as our submatrix, and doing the 2 by 2 determinant, we're going to take the partial with respect to x of our function here on the right minus the partial with respect to z of our function here on the left. And so this function at the start doesn't have any x's, and so its partial is a nice clean 0. And the partial with respect to z of this function is just going to be that same thing, because x and y are constant multiples, and the exponential's derivative is just itself. All right, our last component for our curl. See, now we're looking at k, and we're going to forget its row and its column. 2 by 2 determinant over here. Partial with respect to x of 0 minus the partial with respect to y of this function over here. We're going to get 0 minus x e to the z. And so, putting that all together, what do we have at the end of the day for our curl? We have z e to the z in the x component. Looks like positive xy e to the z in the middle component, and negative x e to the z in the z component. So right there is our curl. And notice this is indeed a vector field. If we plugged in any x, y, z point, this curl would hand us a vector, which we could think of as attached to that point. So just a couple notes about the curl before we start talking about what these things mean. You might have noticed in computing this curl that we're doing a lot of cross partials, right? For example, our last component, the z component, we were taking the partial with respect to x of our y component minus the partial with respect to y of our x component. And indeed, each one of these components has a difference of cross partials. And so actually, if the vector we end up with at the end of the day is the 0 vector, right? This is just a fancy way of saying the vector with zeros everywhere. Well, that would actually be telling us that all of our cross partials are equal. And if you remember back to 16.3, right, that's our indirect check to see if our vector field is a gradient field. So actually kind of a cute theorem here is that the curl of f, giving the 0 vector, that's equivalent to our vector field being a gradient field. This does, though, as it did back in 16.3, it does assume some niceness on the situation that we won't worry about. Maybe just for our notes' sake, let me mention here, right, the curl of f, we made the notice that this involves a whole bunch of differences of cross partials. So if all those differences are 0, that's telling us our cross partials are all the same. And so if we just look at this, this equivalence here, this if and only if statement, if we read it right to left, what this says is that, well, if our vector field is a gradient field, well, then the curl of our gradient field is 0. And it's kind of fun to write down. Another way of saying the gradient field is grad f. And so this theorem is telling us if we take the gradient field for f and take its curl, we're going to get the 0 vector field out of that. So curl grad f equals the 0 vector. Kind of fun to say. Another statement that's also true, you might think, well, what about maybe the other way? What about grad curl F? Well, here this actually doesn't make any sense to write down. Right, curl of F is a vector field, and the gradient, right, that needs an actual scalar function. And so here, this actually doesn't make any sense, but once we have a vector field, right, our first operation today, the divergence, that does take a vector field and give us a scalar function. And so we could actually think about that. We could take a vector field, take its curl, and then take its divergence. And what I claim is that we actually get the constant function 0. And here the number 0, not the 0 vector, because divergence spits us out scalar functions. And the idea here, it's not a super deep thing, since the curl of F involves a bunch of differences of cross partials. Well, it so happens that if we take the divergence of that, we end up with a lot of mixed partials, kind of like fxy and fyx. And those mixed partials are going to match up and just cancel away everything, and we'll get left with 0. And so this is another kind of nice equation that one sometimes sees involving these ideas, these objects. Okay. Well, let's now switch gears from just kind of working with these objects, divergence and curl, and let's think about what these actually mean from a physical perspective, thinking about fluid flow. And so to start thinking about that, let's think back to Green's theorem. Right, in Green's theorem, we had this nice physical interpretation of our vector field giving us the movement of fluid around our region, right? So we have our kind of green vector field vectors kind of showing us how our fluid is moving at each point. And Green's theorem told us, right, that we could either march through the middle of our region, adding up circulation at a point, or we could move around the boundary of our region and ask how the fluid is circulating around that boundary. Right, and the line integral that we computed for that circulation around our curve, right, what it's adding up at each point is the tangential component of our green vector field vector there. Right, so we have our unit tangent, and we take our green vector and project it onto that line, and we grab the tangential component. Right, that's the information that our integral is adding up. Now it so happens that if we make this box small and kind of center it at a point, and we take this integral around this square and let the square shrink, then if we appropriately weight things, what actually pops out is the function qx minus py. And recall that this is exactly what the double integral in Green's theorem is adding up, right? This is our circulation at a point. And so here we see how that function, that idea of circulation at a point, can be somehow obtained by taking circulation around a small square and letting that square shrink. Well, if we change our question now from how is our water moving around to how is our water moving out, well, now at each point we're not interested in the tangential component of our green vector field vector, right? That's showing us how our water is moving, right? So let me try and draw the same vectors as above. Whee! If we want to know how our water kind of around, say, this point is kind of moving away or towards our point, well, now around our square, we'd like to know the normal component of that vector. Right? That would be showing us whether this the fluid at that point is moving in that direction of our normal vector, in this case outward, or if maybe like at this point and if here's our normal vector down here, here our green vector is moving in. And so if we'd like to understand how water is kind of moving out, then what we'd like to add up are the normal components of our fluid vectors as we move around this square. And so if we pick a small square around a point and move around and add up this information, we'll get something. Now what I claim is if we then let this square shrink, then what pops out is the function px plus qy. All right, and this is exactly the divergence of f, right, for a two-dimensional vector field, right, px plus qy. And right, if you believe my little story over here, this is what we get when we take our line integral, where we're adding up normal components and let this square shrink. Well, then the physical interpretation for this is that this is telling us the divergence, or you'll sometimes hear the word flux used at a point. And we can play this game in the plane or in 3 space. Right here, if we're in 3 space, you can imagine us like submerged in the ocean, and once again we have a bunch of these vector field vectors on our box and inside our box, and right, I'll go in every which direction. Well, we could ask, well, how is water, moving out or in of this box? And to answer that question, right, we'd like to go around and at each point on the box, once again, grab the normal component of our fluid vector there. And so here, our normal component is going to be positive since it's going in the same direction. Right? If this green vector was pointed in towards the box, then that tangential component would be behind our normal vector, and so it would be negative. And so what we'd like to do is go through, every single one of these points on the, here's our normal vector there, on the boundary of our box. And we'd like to add up this information of the normal components of our fluid vectors. And if we go ahead and do that, and then let the cube shrink, so and let change in z go to 0, 2, then what pops out is the function px plus qy plus rz. Right, and again, exactly the divergence of our vector field. And so our divergence function, the physical interpretation for it is that it is telling us divergence at a point. In other words, the divergence of a vector field at a point is a number indicating the flow of our fluid in and out of the point. And the idea here being, if the number is positive, then that would mean that there were more vectors, pointing in our normal vector's direction. And so there's got to be more water coming out from our point. And on the flip side, if this number is negative, well, that would tell us that there would be more green vectors like this pointing inside. And so the interpretation here is that there would be kind of more water wanting to come in to that point. And so I'd like to switch over at this point, just for a moment, to a real nice portion of a video from 3 blue, 1 brown, that just gives in about 10 seconds a nice kind of visual, moving example of this idea.
For example, the divergence of our vector field, evaluated at all of those points that act like sources, will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction.
And so again here, the idea is our fluid's getting faster as we move to the right. And so around this point, there's going to be a little bit of water coming in and a lot coming out. And so here there'd be more water wanting to come out. And back here, these points where water is wanting to move out from would have a positive divergence, and the points where water is wanting to move in would have negative. So that's the idea here. But what about curl? Well, curl is a vector field, right? And so we have 2 vector fields going on now, right? We have one, so here's a picture in 3 space, and we have all these green vectors F showing us how our fluid is moving around in 3 space. And again, we can imagine that we're underwater, submerged, and the water is kind of moving around us. Well, the idea of curl is that we want to take fidget spinners. Okay, let's imagine that with us underwater, we brought a gazillion fidget spinners, and through our amazing powers, we send them out to all these different points in 3 space. And so we get a fidget spinner here at this point, X, Y, Z as well. And using our magic powers, we're going to magically hold the centers in place, right, at these points where we have sent them. But now, as we hold the centers there, right, the water, our green fluid here, is still moving. And so each one of these fidget spinners is going to, through the movement of the water, kind of orient itself, kind of level itself out in some direction. And so maybe here at this point, the fidget spinner kind of levels itself out like that. But now, as the water continues to move, right, our fidget spinner is probably going to want to start spinning. And so maybe our fidget spinner is going to start moving this way. Right, kind of spinning around like that. Well, I claim that we can represent all this information, right? How our fidget spinner has oriented itself, the direction that it started spinning, and how fast it's spinning with a vector, right? So the curl of our vector field at this particular point, x, y, z, is a vector showing how a fidget spinner placed at that point would orient itself, what direction it spins, and how fast. Right, and the way that this vector shows you how the fidget spinner would orient itself is that our curl vector is orthogonal to our fidget spinner. Maybe I'll write that. Right, so our curl, that says curl, is orthogonal to the fidget spinner. The direction it spins, well, we can see that using the right-hand rule. Right, and so here, this curl vector is actually going the correct direction, because if you imagine, your thumb, see if I can draw this, pointing in the curl's direction, right, of your right hand. Now, you look at your fingers from your right hand, they're curling this way. And that is indeed showing us how this fidget spinner is going to want to spin. Lastly, how fast our fidget spinner is spinning. This is going to be described by the length of our curl vector. Right, so if this curl vector is super long, that's showing us that our fidget spinner is just going crazy. If it's pretty small, showing that there's a more gentle rotation. But this is the idea that at every single point, we're going to have, one of these fidget spinners down here as well. Right, and each one of these is going to be oriented a certain way and spinning a certain way, and we'll have a curl vector attached to each one. And so the curl of a vector field is another vector field that shows us how at each point all of our bazillions of fidget spinners, how the one at that point would be oriented and spinning. All right, well, that's it for today, looking at the definitions of divergence and curl and these physical interpretations for what these are doing. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.